So today, well, I'm a final year PhD student, and I'm going to just be going through the methodology that underpins my PhD project and the structures that I've been designing. So just as a basic introduction, in 2004, Benzo and Sigmund were finalizing some of the more complex work that underpinned topology optimization as a concept. And they described it as the determination of features such as the number and the location and the shape of holes and the connectivity of the domain. Now, they were talking a lot about some very solid void representations of structures. But what I'm more interested in is the identification of the load paths in any kind of structure as a more grayscale representation of the solution. And what this means is that we can design graded lattice structures that are stiffer than a constant lattice infill. And this also means that we can use the same kind of concept to do the sizing of composite laminates, because the red region will be that's roughly the size of what the composite would be in your design. So the concept would be that we would build these lattice structures using 3D printing, and then we would lay up the composite laminates on top of these printed structures, which would mean that you'd have an internal structural mold, hopefully removing the need for composite tools made out of metal. Can be quite costly and time-consuming to use, especially for wind turbine blades, which is what my work is mostly focusing on. So in the first design stage of this multi-stage topology optimization, we look at just a basic, is that running? Yeah, that's running. So we're just looking at basic, simple optimization, just material agnostic. So we're just looking at where the main load paths are in this structure. And this structure basically tells us for the optimal stiffness, we need 2 spar caps. And we can size our composites based on this, basically by taking all of the low density material in the design and getting rid of it, and anything that's left behind is then the definition of your composite laminate. So then in design stage 2, it gets a little bit more complicated. So for this example, I'm going to discuss a wide box beam under 4-point bending. So here is a thickness optimization that I've used as just an example of stage 1. It just uses the standard sizing optimization in Abacus to give you your shell thicknesses for this structure under 4-point bending. And then we take this skin, we freeze it, and we optimize the internal structure of that box. And here it shows this is the optimal distribution of densities, and it gives you some additional material support where those highest thickness regions were, as well as there's some load points where the 4-point bending loads were applied, which it's given some local support to those, because obviously there's a bit of local force building up there. So once you've got that, you can then immediately test that optimized structure, because it just gives you an output file which you can put straight back into Abacus. And you can see that it fails in the way that you'd expect a sandwich panel to fail. But this managed to actually do a lot better than just a common sandwich panel, so that was nice. And then the design stage 3 is essentially converting it to a lattice structure so that you can 3D print it. So this looks a bit like this once you've converted the design. And I use a program called Lattice, which is made by my supervisor and his research group in Imperial. And from this point, we can import this structure into Abacus. This is a bit of a simplified one because I was having issues with STL files. But this is a linear buckling analysis, just looking at where the first buckling failure mode was. And that gave us a solution for that. And then you can print it, and then you can make it. So that's the methodology. Moving on, future work, hopefully this month, next month, I'm looking at the experimental testing of some hybrid laminate lattice composites. This is a representation, I've got it at my poster. Basically it's just showing you put the skins on the top and the bottom, and you have this optimized lattice shape in between. We're going to be doing some testing to look at how the failure modes happen, and also whether the lattice structure actually performs as predicted. Once we've got this, we can actually extract effective beam properties. So if we look at a longer beam structure, then it starts to have, you can basically approximate your bending stiffnesses and things like that, and then you can put that into a another model, a 1D model, and look at the responses under loading, which will be relevant in a second. And then we'll validate these structures against conventional structures like box beams, composite, sandwich panels under 4-point bending and see how they do in terms of mass. And then this all culminates in looking at blade geometry. So I've got, obviously I showed you a blade geometry before, but I've also got an optimized blade geometry on my laptop, on my poster, if you want to take a look. So this comes back to the effective properties from the optimized structures as well, because this means that you can look at error elastic design if you convert it back to a 1D analysis. So yeah, if you've got any more questions, thanks for my sponsor and all of my supervisors, and I'll see you on poster if you're interested.
Thank you very much, Alex.